So good morning, everyone, to this lecture on machine learning. Today we will be solving some few other questions on naive Bayes and KNN, and also we will going to something called Perceptron model, which is one of the most basic form of machine learning that is available today. Um, we will not go very deep into Perceptron. We'll look at the basics of it, understand the concept behind why the Perceptron model came up in the picture. We'll try to design something called a hyperplane today, and that will help us do some predictions as well. Um, yeah. So let's start. Before that, let's solve a very basic question on DBMS, which is also a part of your syllabus. And just for revision sake, we'll try to solve in each class. We'll try to solve one question from the GATE syllabus that is common to CS and CS and DA. One of them is DBMS. So if you look at the question, given the basic ER and relational models, which of the following is incorrect? Option A is an attribute of an entity can have more than one value. An attribute of an entity can be composite. In a row of a relational table, an attribute can have more than one value. In a row of a relational table, an attribute can have exactly one value or a null value. I'll give you 1 minute to solve this. Okay. Yeah, correct. So option C is the right answer. In every row of a relational table, an attribute can have more than one value is incorrect. That is not allowed when you're looking at a relational model. So as we looked at this earlier, the naive Bayes algorithm was making sure of something that if you have a multi-dimensional data, which means your X comes from a distribution of d-dimensional distributions, right? Which means each xi is nothing but a vector of x1, x2, x3, so on till xd, d features. And one of the main reasons why naive Bayes works because it kinda says that you can do something like this, which is conditional dependence, which means it assumes that you can calculate the probability across each different feature given the label y, and then you can take a product of them to find out your final value of the uh, likelihood, which is p of x given y. So naive Bayes assumes something we call conditional dependence. Okay. Hi Aditya, good morning. Good morning. So this was one lecture. First question we discussed on the prior things that we learned. The naive Bayes assumes something called conditional dependence. The second question is, which of the following statement is false if you have a KNN algorithm? If you look at option C, KNN is used only for classification problem is wrong. It can be also used for regression problem statement. Okay. Okay. If you have categorical variables and you want to find the closest neighbor, which is a distance metric that you will use? So it is nothing but Hamming distance. So this one I didn't teach you, but still let me go through what is this. Typically, yesterday when we were looking at naive Bayes algorithm, right? Um, what we did was, um, so let's say this is your Cartesian plane. You have two classes. One class is, let's say, okay, one class is, let's say, here, and the other class is, let's say, here. Okay, just an assumption. Okay, what naive Bayes was doing yesterday was you looked at each dimension of data. So this is the x dimension. Okay, and then you were estimating a probability distribution across this dimension. Then you looked at the other dimension, and then you are estimating the probability distribution across the other dimension. And then naive Bayes tries to combine these two distributions using the product rule. Okay. Similarly, for the other class, you are doing the same thing. You are mapping it to the dimension space, then having a distribution, and also mapping to the other dimension space and having a distribution. Okay. So if you look carefully, there is actually something called a boundary being created between these two classes. Okay. Which means you estimate the probability given this class, you estimate the probability given this class, whichever it falls to, you assume that is the class that the data follows. But here what happens is, this is something called a decision boundary, which says how likely are you gonna hit this class, the green class, then the red class, or how likely you are going to hit the red class, then the green class? All points lying above this line belong to the green class, and the all points lying below this line belong to the red class, is what it means, very uh, speaking very frankly. Now it is saying that, let's say this is W1 class, and it has a greater prior than class W2 present here, which means there are more number of points that are going towards W1 than W2. W2 will have lesser number of points. So to ensure that W1 gets more number of points, your decision boundary should be somewhere here, so that more number of points fall beyond the decision boundary such that they are classified as green, and more number of points are classified as red, which fall lesser than the decision boundary. So if it is given that W1 has a higher probability than W2, then the decision boundary will shift towards the region R1, or it will shift towards the region R2. If you see carefully, since you want more points to be in the green zone, which is, you'll shift your decision boundary towards the region R2. So that is why in the naive base, if W1 class has a greater prior probability than W2, decision boundary will shift towards region where W2 is there, or region R2. Okay, hope you understood this. If not, I can explain again as well, but okay, I assume you understand. Okay. In a naive Bayes algorithm, the entire posterior probability will become zero when an attribute value in the testing record has no example in the training set. Is it true or false, or cannot be determined? Let's say the posterior probability is nothing but P of y given x is nothing but P of x given y multiplied by P of y. I mean, it's not exactly equal to, because I'm not dividing by the evidence, it is proportional to this. Naive Bayes kind of plays around how will you calculate the probability of P of x given y, where it says that it is nothing but the product of the conditional probability given each feature. Okay, this is what we have been studying since yesterday. Now they are saying that if there is one attribute in your training set, any attribute, let's say x of 1, okay, for that, given the y, there is no record here. Okay, I mean, let's say the y is all no's, but you want to calculate for yeses. For yes, there is no x1 present. This probability will become 0. And if one of the probabilities becomes 0, by a product multiplication, if you multiply 0 with anything, you still get 0. So the posterior probability, which is you're trying to compute this one, will become 0 when an attribute value that is should have been there in the testing record has no example in the training set, which is absolutely true. Okay. This is a question for you. I will give you 5 minutes to solve this question. It's very important to solve because it's very important for the exam. Uh, Please solve this question. If you don't have a pen and paper, let me know then. It's a different issue then. I expect you have a pen and paper with you now. Try to solve this question. I'll give you 5 minutes. We can discuss after 5 minutes at exactly 10:25. Okay, expected you to solve, but fine. Uh, okay, so in this question, you will have to calculate two different things. First, you will have to calculate P of yes given x, and also you have to calculate P of no given x. P of yes given x is nothing but P of x given yes multiplied by P of yes, and this is proportional to P of x given no multiplied by P of no. Okay, so P of yes. Oh, second.
You are currently the only person in this conference.
Okay, so P of yes. P of yes is what? I expect that is easy to answer. 6 by 10. So P of no will be 4 by 10, right? You can calculate, or you can do 1 minus 6 by 10. P of x given yes will be nothing but you take the product of um, P of x1. So x1 is red given yes multiplied by P of domestic. Okay. So second feature is um, type. Let's say type given formal given yes multiplied by P of domestic given yes. So what is P of red given yes? Huh? 5 by 10 is low. 1 second. So there are 11 objects, not. Um, no, there are 10 objects. 2, 3, 4, 5, 6. Oh, they have numbered it wrong. Okay, 5 is repeated. Okay, okay. I think there are 11 objects. Correct. Good observation. 6 by 11, 5 by 11. Right? Okay, fine. What is P of red given yes? Yes. What is the probability that the color is red given that it is satisfied? P of red given yes is nothing but look at all the sets that are present yes. Okay, there are 6 of them, right? Out of these 6, this is red, this is red, and this is red. So 3 by 6 or 1 by 2 multiplied by. What is the probability that the type is formal given yes? You look at all the sets of yes, 1, 2, 3, 4, 5, 6. Out of these 6 instances, how many have a type of formal? If you look carefully, you will see that there are only one type of formal multiplied by. Out of these 6 yeses, how many have an origin of domestic? So out of the 6 yes, if you look carefully, 1, 2, only 2 have, right? Yeah, 2 by 6. Okay. And then you may also calculate, and so this you will get as 3, 2, 2, okay, 1 by 36. Now, P of x given no is nothing but, now your entire thing will change except it will be for the no class. Okay. So what is the probability that your color is red given that satisfied is no? For that, what you will have to do is use a different color. Look at all the instances where there is no. Okay. There are 5 instances where there is no. Out of those 5 instances, where you have a color of red, you can see that only 2 have a color of red multiplied by. Again, you look at all the rows of no, because this is conditional probability. You're conditioning on some event. Condition means the given that the event no has occurred, so you do not consider the yeses at all. Given that the event no has occurred, what is the probability that the color is red? Given that the event no has occurred, what is the probability that the type is formal? Given that the satisfied has no has occurred, what is the probability that the origin is domestic? And why am I looking at red, formal, and domestic only? Because that is what is asked in the question. Given that the color new object has a properties, color as red, origin as domestic, and type as formal, you need to tell me that which class does it belong to. Okay. So look at the all the no's and try to find out which are formal. If you see 2 out of 5 again, and domestic you will see 1, 2, 3 into 3 by 5. Correct? And if you calculate this value, you will get 12 by 125. So now, you can now calculate the value of this one, which is 1 by 36 into 6 by 11, which is 1 by 66. Okay, I have exceeded annotations. Okay, let me remove this thing then. Okay. Okay. Then you get 1 by 66. And for this one, you will get 12 by 125. Okay, so let me remove the yes part because I'm exceeding annotations. 12 by 125 into probability of no, which is 5 by 11. Okay, so if you try to calculate this value, you will get uh, 12 by 275. So one probability is this, one other probability is this, and if you quickly do the math, 1 by 66 is 0.01 or 0.02, I can say. 0.02 versus 0.04. Okay, so this is about 0.02, this class, yes class, and the no class is about 0.04. So you can declare that he or she will not be satisfied. Okay. Okay. So today, as I said, we will look at something called a Perceptron model, which was the first machine learning model that was invented in the industry. It is a very, 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 very simple model. It's very simple actually. But still, there are some intricacies involved here as well. We will try to look at those, okay? And then we will try to find out what we can do in this case. So, perceptron model has two assumptions. So KNN had an assumption that points that are close together, they have the same label. Naive Bayes has an assumption that the features are conditionally independent. Perceptron has two assumptions. One is you will only look at a binary classification, which means your y belongs to -1 comma +1. It could be anything, 0 1 or 1 2 or anything. In this example, I'm taking y belongs to the class either -1 or +1. The second assumption is that the data is linearly separable. What do I mean by linearly separability? Let us look at by a simple example. Let's say this is a graph and there are two classes. One is this one, and the other class is this one. Okay. These two lines, these two classes, I can claim are linearly separable. Now, how are they linearly separable? I can draw a line between these two classes. Okay. And I claim all the points that lie above this line, all the points that lie above this line belong to one class, and all the points that lie below this line belong to the other class. That is what I mean by linearly separable. You can separate out the two classes by drawing a line between them. So, what the perceptron model does is it tries to find out, it again tries to find out one of these lines. Okay. For a two-dimensional space, it is a line. For a three-dimensional space, it is called a plane, and similarly. Okay, that I'm not going through now, okay, because of lack of time. But the basic funda of perceptron model was given a data that is linearly separable, your objective was to find out the line that separates these two classes. So how it kind of worked out was, so if you extend this line beyond, I'm not able to do it. Okay, let me see. Yeah. Okay. So if I extend this line beyond the axis and touch it to the y-axis, then let's say that this line has a perpendicular called W, which is also called the weight vector. And if W is perpendicular to this line, then I can claim that W transpose X, which is the dot product of W with X is the um, set of features, set of your data, plus a y-intercept, which is B, should be equal to 0. This is the equation of the hyperplane. If I have a perpendicular vector W, okay, if I have a perpendicular vector W, then this equation W transpose X plus B is 0. The proof is very long. This was taught, I guess, in your high school and college as well when you studied vectors. Proof is very long, so that is not something that I'm willing to do now. But if you don't understand this, that's okay. You can just look at this, that any vector perpendicular to a line will have the equation W transpose X plus B equal to 0. And what does the Perceptron algorithm now tries to find out is, it tries to find out the values W and B. So let us define a hyperplane. So a hyperplane H is nothing but X such that W transpose X plus B will be equal to 0. This is your hyperplane. Okay. And your hyperplane, what it does is, as I said, if this line defines your decision boundary, then W transpose X plus B is 1 if this is greater than 0. It is minus 1 if it is less than 0. So if the value of this equation is greater than 0, then I fall above this line. Then I am above this line. In that case, I can say that the output will be 1. And if it falls below this line, then I can say that the output will be minus 1. Now, typically, so let me again formalize the setting. You had your set of data points x comma y. Your y should only belong to a binary classification scenario, which is minus 1 comma plus 1, right? And your hyperplane H is X such that W transpose X plus B becomes 0. And now your job is to find out the values of W and B. Now, learning two things is a hassle. It's something that you would not want to do, let's say. So the designers of Perceptron came up with a very, very nice trick. What I can do is, if I have a vector xi, I just add a new dimension and I say that all the features remain as it is. Only I have another dimension whose value is always 1. Okay. And my weight vector W is now mapped to whatever it was earlier and B. Okay. So now my hyperplane equation is modified to X such that W transpose X is equal to 0. And if you take this W, which I have written here, W and B, and if you take the dot product with xi and 1, you will realize that you will exactly get the same thing, which is W transpose xi plus b. Okay, so it's the same setting, only instead of learning two things, now what we will do is we learn W, which is the thing that is kinda, you can say, encapsulating B in it. Okay, fine. So when I say that my W transpose X is 0, which means I do not have a y-intercept for W, right? It's more like W transpose X plus 0 equal to 0. So that then I can also claim that my W passes through the origin. This is my W, okay? Because I don't have a y-intercept now. So now let us look at the algorithm on how to find a suitable W. Okay. The first step is to initialize W as a zero vector or W to all zeros. Okay. The next step is the next step of the algorithm is you will iterate till while true, like an infinite loop. Just a minute, my iPad has battery less. Disconnect my charger. Okay, awesome. So I will iterate till while true. Okay, yeah, fine. I will iterate till while true, and what I will do is first I will have a counter which is m is 0. This counter denotes the points that are misclassified. What do I mean by misclassified? Which means initially when whatever weight vector you assumed or whatever is the status of your weight vector, you are trying to train a model. Okay, if your y is, let's say, +1, which means your true output is you should belong to the positive class, and your W transpose X gave a value less than 0, which means your W transpose X is trying to say that the answer is -1, but in the true sense your answer is +1. This is a misclassification. On the other hand, if your true value y is -1, and your W transpose X gives a value greater than 0, that is also something called a misclassification, because your true output is negative, but your model is trying to predict positive. Okay, so that is nothing but a misclassified point. So the third step is you iterate over all your data points for all x comma y belonging to the data set D. Okay, if, again, please pay attention here, it's a very important thing and very interesting as well. If y times W transpose X is less than or equal to 0, then my claim is this denotes a misclassified point. So first you increment the misclassified point, and then you update the weight vector W plus yx. And then 6, if m is equal to 0, then you break from the loop. So You initialize the weight vector to all zeros. You initialize a while loop, true. Initially, you have a pointer m equal to 0 that specifies how many points are misclassified. And then you iterate over each x comma y in your data set. And if y times w transpose x is less than or equal to 0, then again, please hold on, I will let you know why. Then you increment the misclassified point by 1 and you update the weight vector by w becomes w plus yx. At line 6, if m is equal to 0, which means if there is no data point in your data set that is misclassified, that means you have found your hyperplane, which is every point has been classified correctly, negatives fall in the negative space, positives fall in the positive space, then you can break from the loop. Now, the entire jigsaw puzzle is to find out why does this work? Why does this if condition work? Now see, suppose y is plus 1. Suppose y is plus 1. And your W transpose X, the output from your model, is also greater than 0. Okay, again I see the notations. Let me remove this. Okay, is greater than 0. So plus 1 and positive. So positive times positive is positive. Okay. Let's say that your true value is minus 1. And your W, okay. Okay, then maybe I'll just speak it out. So let's say your y is minus 1 and your W transpose X gives the value less than 0, which is negative. So negative times negative is positive. So whenever you're trying to classify the point correctly, then it will be positive. Y times W transpose X will be positive. But let's say if you're having a positive class, right? And your W transpose X is less than 0, which is negative. So positive times negative is negative. Here, if your W transpose X is greater than 0, which is positive, but your true label is minus 1, which is negative. So negative minus multiplied by positive is again also negative. So then you can claim that your point is misclassified. And with that, you update the weight vector. So how does it help by updating the weight vector? So the other thing about this jigsaw puzzle that we tried to find out was W became W plus yx, which means if y is positive plus 1, then you are adding W plus x. If it is negative, then you're subtracting x. Okay. Natural question will be why does it work? Okay. Or how does it work? Let's say that there is a point x in the hyperplane. Let's say this is a point x. That is actually the y value of this is plus 1. The true value of it is plus 1. And let's say that you have okay, fine, thing doesn't work. And let's say you have a hyperplane. This is your current hyperplane. This is your origin. This will be your weight vector W. Okay. This will be your weight vector W. According to this setting, what will your model predict? What will be the value of W transpose X? Is it less than 0 or greater than 0? Yes. If you see carefully, this X vector falls below the line. Yes. So your W transpose X will be less than 0, and your y was plus 1. Your true value is plus 1. So this is a misclassification. And accordingly, what it will do is it will try to update w with w plus x, which is vector addition. So let's say this is the vector x. So you just replicate it here, vector x. And now if you do the addition, vector addition, this is your new vector w plus x. And now your hyperplane is something like this. Okay, this is your new hyperplane now. W dash is your new hyperplane. And now if you see carefully, your point X lies above the hyperplane. So next time you can see that the point is actually classified correctly. Because your W prime transpose X will be greater than 0. And that is what you want as well. So that is how it works. So the last thing that I will discuss on Perceptron, and in fact of today's class, is something very, very important. A bit long it will be. A natural question to ask is, will the Perceptron algorithm always converge? Which means, given a set of data points, does the Perceptron algorithm converge? So to answer this question, we will have to look at some setting. Okay, we will try to formulate this problem first, and then we try to prove it. The first assumption that I will make to prove this is that the data is linearly separable. If the data is not linearly separable, then my algorithm will just keep on looping around the points, trying to find the correct hyperplane. It will never be able to find it because there is no linear separability. And then your algorithm will never converge. So I assume that my data is linearly separable, and then I can say that the perceptron algorithm will converge. Which also means that I claim that there exists a hyperplane. I'm calling it W star, which denotes the hyperplane that actually separates the two uh, classes. There exists a W prime such that for all dataset values x, y belonging to the dataset capital D, y times w transpose x is greater than 0, which means w star transpose x is 0, which means all points are correctly classified. Okay. And another assumption I make is that the norm of w is 1. What is a norm? Norm denotes the length. So if you have a vector v of, let's say, two elements v1, v2, the norm of v is nothing but root over v1 square plus v2 square. Other term that you might have heard of is called magnitude of a vector. It's the same thing. And another assumption that I make is I also standardize my data points. So each xi's norm is also less than or equal to 1. It is at most 1. for all xi comma yi belonging to D. So what is my assumption? First assumption is that data is linearly separable, which means there exists a hyperplane W star, there exists a line, hyperplane might be a scary word, so let me say it is a line, W star, such that for all data points x comma y in the data set D, y times W star transpose x will be greater than 0, so that they are correctly classified. And the norm of W that I'm trying to find, norm of W star, in fact, that is a optimal hyperplane, is 1. And each data point I'm standardizing it such that the maximum value is at most 1 for all data points xi comma yi belong to D. And how to do this thing? You can calculate the max norm, okay, which could be the max across each dimension, the norm of x, and then you divide xi by the max norm. Okay, then you divide xi by the max norm. Okay. The second thing that I will assume here is that there is something called a margin. Let me denote that by gamma, which denotes the minimum across all data points xi comma yi belong to D, such that the distance of that point from the hyperplane, right, the distance of that point from the hyperplane is minimum. So what do I mean by this is, if I look at any simple sample data, let's say here, across all data points, the point that is closest to the hyperplane is this one. And so this is my margin. And my claim is that every point in this data set lies at least gamma distance from the margin. Why? Because from the hyperplane. Why? Because if I claim that gamma denotes some minimum distance between the hyperplane and a point, every other point will have at least a distance of gamma, because if it does not have, then that point will be forming the gamma. So if I designate that gamma denotes the smallest distance between a point to the hyperplane, every other point in the data set will have a distance margin greater than equal to gamma. Okay. Okay. So these are my two assumptions regarding the data set. Okay. Assumptions in the sense, only there is one assumption, which is data is linearly separable. Others are just calculations that you can do in order to form this proof. Okay. Again, I'm teaching this proof because I don't know whether they will ask. They could ask because it's very important for the exam. But still, so for completeness sake also, it's good to know. Okay. Okay. Now, the theorem of convergence says, just a minute, I think. So the theorem of convergence says, if all above conditions okay, maybe I have to write it on the next slide because okay. So the theorem, do I have extra slides as well that I can write on? Yeah, okay, good. Okay, so the theorem says if all the above conditions hold true, okay, then the algorithm or the perceptron algorithm converges in at most 1 by gamma square iterations, where gamma denotes your margin. It will converge in at most 1 by gamma square iterations or 1 by gamma square steps. Okay. Now, to prove this, after each update of the perceptron model, we will try to find out the update across two vectors. One is the vector that I'm trying to find, W, its relation with the with the correct vector, the vector that linearly separates it, and the relation of W with itself. Okay, we'll try to find the relation between these two to find out that what is the issue. So again, why do we do this? Again, hold on, I will explain. Once we look at the proof, it will make things a bit more simpler. And I'm absolutely okay if you don't get it in the first try, but still bear with me. If you go back and again watch this lecture, you will be able to understand things very carefully. I assume you know all these things, which is the similarity between two vectors is nothing but the dot product, and dot product is given by this notation. If you don't know this, then maybe you can revise this and then try to look at this video, and then it will be much more simpler. So the proof is when you are updating W. When you are not updating W, then it's okay, you are not doing anything. So you will update W means the W will now become W plus YX only when the point is misclassified, which means Y times W transpose X is less than 0, less than or equal to 0. Okay, because if Y times W transpose X is greater than 0, then you are not updating it in the first place. Okay. Now with this update, what does it happen for the different weight vectors? So first let's look at W transpose W star. So W has become now W plus YX transpose W star. And this is nothing but W transpose W star plus YX transpose W star. Okay. Plus this is Y into X transpose W star. Now, if you look carefully at what I wrote here, again, there's a very small thing I missed here, which is the margin. You can say the margin as Y times this because margin is positive, right? So what I mean to say is xi times W could be positive or negative depending on where it lies in the hyperplane. And then if I multiply it with the if I multiply it with y, then I will get the positive value always. So this is my y times xi transpose W. And if you look carefully again, here also it is the same, except this denotes for each x. So I can claim that since since gamma denotes a minimum such value, so this value could be at least greater than or equal to W transpose W star plus gamma. Gamma is the minimum value possible, and this value will be at least greater than or equal to that. Either it will be equal to or greater than that. So that's why I can claim that this is plus gamma. Okay, fine. Now, what is the effect on W transpose W? W transpose W will now become W plus Yx transpose W plus Yx. And if you do the dot product of this one, you get W transpose W plus 2y W transpose X plus y square into X transpose X. Okay, if you do the dot product in this scenario. Now, if you look carefully at this point as well, right? As I claimed now that in my assumption, another assumption that I claimed was the norm of X is less than or equal to 1. Correct? My norm of X is less than or equal to 1. It cannot exceed 1. And X transpose X denotes X square. So this is also less than or equal to 1. And even if y is negative, y square becomes positive. And 2y W transpose X will also lie between 0 and 1, because if the point is misclassified, then this thing is less than 0. So what I meant to say is not 0 to 1, this is less than 0, because less than or equal to 0, because you have misclassified this point. So y times W transpose X is less than or equal to 0 as per this assumption. And also this y square X transpose X is at most 1. So I can also say here that, claim here that this value will be lesser than or equal to W transpose W plus 1. I can make an estimate that whatever it is always less than or equal to W transpose W plus 1, because this value is less than 0. This value is maximum 1. It cannot go beyond 1. So I can say that if this is, let's say, 0, if let's say this is 0, because that's the best one you can get, and this one is 1, so at max you can only increase it by 1. Okay. 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 Now with these two things, if you look carefully, whenever I update for the first time, I increase W transpose W star by gamma. When I update it once again, then it becomes 2 gamma, 3 gamma, 4 gamma, 5 gamma. So if I'm doing a set of M updates, then my W transpose W star, I'm increasing it by M times gamma. Okay. And similarly for W transpose W, if I update once, it updates by 1, because it's W transpose W plus 1. I again update it, so it's plus 2, plus 3, plus 4 till plus M. So I can claim that after M updates, my W transpose W star will be greater than or equal to M times the gamma, and W transpose W is less than or equal to M. Okay. So if I take this first equation and I am just writing it in reverse, so M gamma is less than or equal to W transpose W star. Now, if you have forgotten, the dot product of two vectors is nothing but W transpose the norm of it, W gamma the norm of it, multiplied by the cosine of theta, right? I mean, that is something that we learned in high school. Now, my assumption at first was the norm of W star is 1. So this I can write this as W transpose cosine of theta. And if you still don't recall your trigonometry, then cosine of theta can be less than or equal to 1. It has maximum value of 1, minimum 0. So we can say that this is less than or equal to W transpose. Okay. So this is nothing but, since cosine of theta is at most 1, and this is also called the Cauchy-Schwarz inequality. Okay. Okay. Fine. So this is nothing but the, and also another thing is the norm of W transpose is the same as norm of W. So let me write this as norm so that you don't get confused. Okay. And I can write this in the form of a norm as root over W transpose W. And what is W transpose W? W transpose W is nothing but M. So less than or equal to root M. If you substitute equation 2, so let's say this is equation 2. And then when you equate these two equations, M gamma is less than or equal to root over M, you will get that M is less than or equal to 1 by gamma square, which is the proof that says when you run the perceptron algorithm, and assuming that your data is linearly separable, which means a W star exists, then your maximum number of updates that you will do on M, which is M, is less than or equal to 1 by gamma square. Again, my job was to teach you how to do this proof and what is the proof, and also to tell you that the perceptron algorithm will converge always given the data is linearly separable. Again, the assumption is given the data is linearly separable, this, let me be very honest, this won't be very important for your exam because I don't see any question being asked in the gate. I mean, they could just ask that what is the number of updates given the margin or something like that, but it's good to know, right? If you don't understand, then don't be afraid. Don't be afraid of it. It's absolutely okay. Main thing is to learn how to. But if you know this, then I can say you are a master in this algorithm. So main thing that we should know is the how to find the hyperplane, which is the convergence criteria, and how the algorithm works, because they might give you some data points and then tell you, can you find out a particular hyperplane given this data point? And so if you still want to learn, maybe watch it again. You will definitely get it. It was not very easy for me as well at the starting, but gradually I understood it. Okay, fine. Okay, so we'll do some practice questions on perceptron before I end this class today. Okay, we'll solve 3 questions. I guess 3 we have, not more than 3. Let me see just once. 1, 2, 3. Yeah. So I have 3 questions and then we will end the lecture. Okay. So a perceptron is guaranteed to learn any set of training data given a suitable learning rate. So just forget about the learning rate for now, that I will explain when we go into gradient descent and all that. But for now, just forget about it and read this as a perceptron is guaranteed to learn any set of training data. Is it true or false? The answer to this question is false, because be careful. Even if I showed you a whole convergence proof in the last slide that the algorithm will guarantee to learn any set, but uh, the assumption that is that the set of training data is linearly separable. This question assumes it can learn any set of training data, which is false. Now, imagine that you trained a perceptron model and you, after learning was completed, you discovered that the data were all labeled backwards, which means every example that was labeled 1 should have been a 0 and vice versa. So whatever was positive was actually negative, whatever was negative was actually positive. Sadly, you no longer have access to the data and you have no ability to change the code that uses a perceptron to flip its answers. So you do not have access to the data, neither you have the ability to change the code. All you have access to are the weights of the perceptron. You have the weight vector. How would you change the weights in order to flip all the answers? You may assume that there are no data points that fall exactly on the boundary of the two categories. So they are saying that you have trained a perceptron model looking at some data. Your data, you have trained the perceptron. Later on, you found out that actually the fact is the data is swapped. I mean, whatever was positive was actually negative, whatever was negative was actually positive. You do not have access to the data, neither you have access to the code to use the perceptron. All you have is the weights of the perceptron. So how would you change the weights in order to flip the answers? So your y was positive, your w transpose x was positive, and you predicted yes. Your y was negative, your w transpose x was negative, you predicted no. But later on you found out that this was actually y equal to negative. So you need to make sure that your W transpose X is negative as well. So what can you do is you can negate the weights. If you have access to the weight, they are saying you have access to the weights, you can negate the weights such that your predictions will be flipped. So y equal to positive minus W transpose X becomes greater than or equal to 0, less than or equal to 0. And now the problem could be that they are saying that if it is equal to 0, then you actually don't know where you want to go, whether it's a positive or a negative class. But they are saying that you may assume that there are no data points that fall exactly on the boundary between the two categories. Understood? You just flip the signs of the weight vector. Positive becomes negative, negative becomes positive, such that you can now get the correct answer as well. Very interesting question. Okay, so consider a supervised learning problem that has two examples where each is a point in a five-dimensional space. The first example is the vector 15279. There should be a comma here and has a label of 1. And the second is -3, -8, 2, 4, 6 and has a label of 0. Give two distinct perceptrons that would correctly label this point. Let's not go with two perceptrons. Let's say we're trying to find only one perceptron. Okay. So what I'll do is let me set up the problem. So each xi is now whatever vector I have xi, then 1. So my x1 is 1, 5, 2, 7, 9, 1, and my x2 is uh, -3, -8, 2, 4, 6. Y1 is 1 and Y2 is 0, but I will say -1. Okay. My model, if it outputs -1, I can say the output 0 for that case. Okay. Fine. My W initially is zeros, and the size of the W should be the same as the size of the size of the W should be same as the size of the data set 6. So 6 zeros. Okay. Okay. Let me know if I'm breaking anytime. My voice maybe it was showing loss in connection. Remember. Okay, fine. Okay. So first you try to calculate W transpose X1. You will see it is 0. Right? If you take the dot product of W with X1, you get as 0. and your output should have been 1, correct? Output should have been 1. So it's a misclassification. So what you will do is you will update the W as W will now become W plus X. So you will just add the uh, X1 to W. This is my new W. Okay. The next iteration, you will try to find W transpose X2. And W transpose X2 is what it will be. You can calculate it. Oh, sorry. I think this should be 1 as well. So 1 plus 6 times 9 is 54 plus 28 plus 4 minus 40 minus 3. So if you calculate 54, 74, 82, 83, 87, 44. This is also greater than 0. So it is a misclassification because the point is actually -1, but you are outputting as +1. So you will have to update the vector by subtracting the value of x, which becomes -2, -3, 0, -3, -3, 0. Okay. So you again go ahead and try to find W transpose x1, and W transpose x1 will be -2 plus -3 times 5 is -15 plus 0 0 है, -3 times -7 is -21 plus -3 times -9 is -27, and you will get some value x. Then you have to again see that this is also less than 0, so you'll have to add the value x1 to it. This one is oscillating, so if you again go through this set of data points, if you don't find the set of data points after some iterations, you can say that it is not linearly separable. Again, you cannot plot this on the graph because it is a 5-dimensional space. Okay, so just this is one thing that I can say. Just how to find out the weight vector is keep on iterating. Try to find if you correctly classify, then don't update the weight vector. If you incorrectly classify, then you update the weight vector. Okay. The problem with this approach is there is something not mentioned called eta, which I have also not told, which is called learning rate, which is how much you want to increase the W. So what is happening is, so this is W. Okay. And this is the best part where the error is where there is no error. Your W is initially here, you are incrementing by x, so you went here, you are again decrementing by x, so you went here, incrementing, decrementing, incrementing, decrementing, you are never reaching the point here. So what you can do is you can take a smaller jump, go here, take another smaller jump, go here, and that is why your learning rate is important, but that we will learn later, don't worry about that. But this is what it is. About perceptron model. Oh, sorry. Uh, just a second. Why is this? Okay.
You are currently the only person in this conference.
So before ending this lecture, I will just one small interesting fact about perceptron. So perceptron was the oldest algorithm for machine learning. It was the start of artificial intelligence, started in 1958 by someone named Frank Rosenblatt from Cornell. What he did was, he said, if I have two classes, okay, then I can draw a hyperplane, that is a line that separates these two classes. Positive part point here, negative part fall below the plane. It was a very good research work done by them, and it gained a lot of traction. Okay. I mean, people were just talking about it every time and all, until someone in 1967 came up with a simple uh, problem to this approach. What he did was, he said, this graph, very simple graph I will draw here. Um, x is, let's say, 0, x is 1, x is 0, x2 is 1. Okay. And what he said was the function, so this is x2, this is x1. The function between x1 and x2 will be x1 XOR x2. So you will do the XOR operation. So 0 XOR 0 is 0. So you fall here. Okay. And let's say that 0 is denoted by a class. So this is your 0 class. Okay. And 1 XOR 1 is also 0. So you fall here. Okay. And 0 XOR 1 is 1. So you fall here. And 1 XOR 0 is also 1. So you fall here. Now, no matter how much you try to do, no matter what you do here, any hyperplane you draw, let's say if I draw a hyperplane like this, or like this, or like this, or like this, or any hyperplane you draw, you will realize that you will never be able to separate these two classes. In the sense, let's say I draw a hyperplane like this, okay, and you claim that the points that lie above here are positive, which is not the case because you have reds here. So you might think that, okay, fine, what I can do is I can make a hyperplane like this. And points lying above this are positive, so which is correct. But points lying below this are all negative, but this is not negative. So, and if you again try to draw any hyperplane, you will never be able to find out. Okay. So he argued that we are talking about a very revolutionary research work done by Frank Rosenblatt. But that revolutionary research work can never actually try to find a model that can estimate this data. So how can I be sure that it will be able to do for large data sets? Correct? And this paper was the start of something called AI winter, where people stopped talking about AI. Since many years people never talked about AI, thinking this is a sad, this is not a very interesting work, because if it is not able to do something so simple, then there is no point of talking about it. Until in 1991 or 1992, when they said something called ML. I mean, they just renamed AI and called it machine learning now. And they found, they what they did was they that tried to beat someone at chess. The algorithm actually defeated the world champion of chess, and sadly, the world champion of chess died soon after, and that was the start of ML actually. So Perceptron was one of the breakthrough researchers in ML. Perceptron was killed by a person who had a very good argument saying this is the reason why I think it's bogus, it's bullshit. And then, after some years in 1992, someone created a model that beat the world champion of chess, and that's why, and he coined a new term saying we don't do AI, because someone else might again come up with this example and say, oh, you're doing something that can't linearly separate XORs. So he said we are doing ML, which is a renaming of AI. Okay, so that is the story. So this won't be asked in the gate. They might ask you a question that if, let's say, f of x1 x2 is the function x1 XOR x2, is it linearly separable? Your answer is no. So again, one homework that you can do is you can also look at x1 or x2, x1 and x2, And if you can find a graph that can linearly separate or an and, that will be also a very interesting thing that you can find out for your exam as well as to better understand this algorithm. Okay. With this, I will end my class for today. In the next class, we will talk about regression. I had promised we will talk today, but this was something that was I left. I somehow missed this talking about this algorithm, Perceptron. But don't worry about it. I won't go through much math from now. This is the most math that was there for Perceptron, but there is math involved in ML. So if you run away from math, then you're also running away from ML. So, but still, it won't be as intensive as this one. So don't worry about that. Okay. Next class, we will talk about linear regression and logistic regression, and we'll learn some more important concepts like gradient descent and all that. That thing that will make you 40 to 50% setup for your exam. Okay. And then the last thing that will remain is decision trees and the feed forward neural network.